So, Abdul, could you say something so we make sure we can hear you, please?
Yeah, I'm here if you can hear me.
Okay, great, thank you. So sorry, so I just want to make sure. So we're recording and everything's okay. So thanks, Fabio, again, and we'll start now with our second speaker of this morning's session, who's Abdul-Latef Haji-Ali. So it's known to many of us here at KAUST because he did his PhD here at KAUST. And he also did, followed by a postdoc at the University of Oxford, and now he's an associate professor at Heriot-Watt University. He's going to be speaking on hierarchical and adaptive methods for efficient risk estimation. Thank you very much, Abdul, for accepting to speak here, and please take it away.
Thanks, AJ, for the introduction. Yeah, and I'm quite dismayed that I'm not able to join you in person, and I'm having to give the talk online. But yeah, I will try to keep it brief and get back on time in the schedule. So as AJ said, I will be talking today about hierarchical and adaptive methods, in particular for credit value estimation, which I'll discuss in a little bit. This is joint work with Mike Giles and Jonathan Spence, and I should say as well, the adaptive part is also with Arita Teckentrup. And although the main part of the work will be with these two authors, and actually I should credit Jonathan with most of the work here, including preparing the slides. Right, so let me first motivate the problem, and I'll take this slow so you don't have to read it quickly. So we have this particular what's called credit value adjustment, which is a particular value that banks like to calculate, which takes into account the risk of a counterparty defaulting on a counterparty who they are involved in with an option, defaulting on their obligations. So you see it's a nested expectation in the neutral measure, where the first expectation is conditional at the stock price, ST, and what's called the credit spread of the party, which is a measure of how likely the party is, or how tenacious, or how precarious, I should say, the position of the counterparty is. So conditional on this, there is a default time. Sorry, there's a default time tau t, which tells you when the party is going to be defaulting based on the current market values and the current position of the counterparty. So this will tell you when the distribution of when the party will default, and then one can draw a random sample of the default time, and then conditional on this, one can compute what's called the exposure, or the exposure at default. So conditional on the market at the default time and the default time, what is how much will the bank lose in terms of the value of the option? So this, of course, the bank will only lose if the value of the option is positive. Otherwise, they won't lose anything. There is a discounting factor, and obviously, I'm only interested in the default up to some final time. And there's an additional factor here. It's called the loss given default. Typically, the bank will not be losing all the value of the option, but some proportion of it. And so this could be, for example, 0.8. So the structure here, the interesting structure is that it's a nested expectation where you have the market price, conditional on market price in the first time, and conditional on both the defaulting time and the conditional price, and the market price and the second expectation as well. And in fact, this already presents a challenge that is addressed in other works, and I'll address it here briefly. But the more challenging part is if one is interested in computing risk measures based on this quantity of interest, the credit value adjustment. So what we're interested in is what is the difference in the credit value adjustment at some short risk horizon H, and how does that increase relative to the credit value adjustment at time 0. So this difference here will depend on the physical market properties. And so this jump, if this jump is large, it means that the relative to some fixed value, then this will mean that the bank's position is also precarious, and they need higher capital to cover any potential losses. So what we're interested in then is computing these risk measures, for example, the probability of this quantity of interest, again, the difference between these two, now with respect to the market at SH and the credit spread at H. So the probability that this difference is larger than some fixed value. And then once you compute the probability, one can compute the value at risk or other conditional value at risk or other risk measures relative that are concerned with this quantity of interest. Okay, so that's the motivation. And in the next second slide already, I'll strip all the financial bits and just focus on the structure then in terms of functions. And so if you are not interested in the finance part or not interested in the motivation, I'm going to be introducing here the problem in terms of just functions and probabilities and expectations. So overall, our goal is to compute the probability that some function of the market of a stochastic process SH is larger than some fixed value. Yeah. And this lambda of SH is computed as an nested expectation. So an expectation of a function f with another expectation of another function pi. The function pi is evaluated at the market price at maturity, while we're conditioning at some the value of the option, the value of the market price at some random default tau, and conditioning on SH being the market at time at the risk horizon H. So the stochastic process, as I said, is the market process. Well, here I have some assumptions. F is piecewise linear, and that's just to connect it back to the F I was interested in before. Here I had the maximum. So I'm only interested at this juncture in piecewise linear functions, continuous piecewise linear, I should say. Tau is has a particular, so it's non-particular probability distribution for a given SH. And here I am also hiding the credit spread. It doesn't really affect anything. So I'm just going to capture everything in this SH. And finally, this lambda SH is what I had before, which is expected exposure. I'm just going to call it its the losses given the market SH. So instead of having two expectations, nested expectation, we actually have three here. We have the probability over the market measure and two expectations over the neutral measure. And we have all sorts of functions. So with the probability, we have a discontinuous function. In this one, we have a Lipschitz continuous piecewise linear function. And typically, pi could be twice differentiable or Lipschitz function. Okay, so that's the problem. And just to give you an idea of, so typically the way that this CVA problem is solved is actually through a series of approximations, assuming everything is normal, and then computing simple sums. And that's because the Monte Carlo method is very expensive. So the Monte Carlo method, an accurate Monte Carlo method would require, of course, sampling this lambda functions, the expected losses for different stock prices in the physical measure at H, and then evaluating the indicator function and then summing up M of them. Now, the number of samples will be, of course, order epsilon power minus 2 for a root mean square epsilon. And for the losses, if one can compute, if one has to approximate both the number of samples, the stock price, let's say at SH as tau and ST, one would use Euler-Maruyama Milstein discretizations, and then you would have to maybe use Monte Carlo samplers for both of these expectations. And the Monte Carlo samplers will introduce 1 over n, where n is number of samples, bias, while the discretization of the stock prices will introduce an order h bias. So in order to kill off the bias, you would need an order epsilon power minus 3 for both two expectations and the stock market, the stochastic process, I should say. So for all these three, you would need an order epsilon power minus 1 cost. So the total cost will be epsilon power minus 3, so summed up with or multiplied by the number of samples here, epsilon power minus 2, you get epsilon power minus 5. Now, you will see that I will be using unsurprisingly multi-level Monte Carlo. And one issue with multi-level Monte Carlo, if I apply it at this level here for this expectation, is that this indicator function actually reduces the cost. So it reduces my variance convergence rate. In particular, if I have two approximations of SH and any two approximations of lambda as a whole. If I have two approximations of those, and those approximations fall on different sides of L, then I will be making an order 1 error. And this will correspond to a reduction in the variance reduction rate, which will correspond to suboptimal multi-level Monte Carlo. So in order to solve both of these problems, for the first one, in order to sample this lambda at an order epsilon power minus 1 cost rather than epsilon power minus 3, I will be using a recursive unbiased multi-level Monte Carlo. So I'll be using multi-level Monte Carlo for this expectation, and for this expectation, I'll make it unbiased for easier handling. And in order to deal with the indicator function here and recover the optimal complexity of multi-level Monte Carlo, or near optimal complexity of multi-level Monte Carlo, I'll be using adaptivity. Okay, so let me start by reminding you of what you already know and remember, and that is talking about unbiased multi-level Monte Carlo. So unbiased multi-level Monte Carlo is based on and just to set notation and mention some things that I'll refer back to later on. So it's based on this this correction, just like multi-level Monte Carlo, where you have the difference between two quantities of interest y approximated at two different levels, L and L minus 1, and then writing the expectation of y, which we're interested in, as an infinite sum of all these corrections. So assuming that this difference here converges to 0, meaning that the bias converges to 0, this is a valid way of writing, subject to some bounds. This is a valid way of writing the expectation of y. And then what I'll be doing is I will, under certain assumptions, I'll take the number of levels, the level number L to be a random number, and then to be able to write this infinite sum as just a single expectation. So the single expectation will be the correction delta y L divided by the probability of choosing that level L. So I can write this. This is just in a simple expansion because the probability, the inverse of the probability of choosing the level L cancels with the probability of choosing the level L itself. So this now is a representation of this infinite sum, and this only works under certain assumptions, mainly the typical ones of the cost and the second moment of the delta y of the corrections. So the cost, I'll assume it's 2 to the power gamma L as usual, while the second moment, I'll assume that it converges like 2 to the power minus beta L. And crucially, I need beta to be greater than gamma in order to be able to write this. And the reason why I need beta to be greater than gamma is this is now my new random variable that I'm focusing on. And what I will be doing is I'll approximate this expectation using just simple Monte Carlo now with this new random variable. So whenever this new random variable requires sampling the random level of approximation L, and of course the underlying stock price or any random variables that are involved in the calculation of y. And I want this random variable to have both finite sampling cost, so that my Monte Carlo's approximation of this expectation is is just proportional. The cost of the Monte Carlo is proportional to the number of samples only, so that's why I need to find sample cost. And I also want sample variance, the variance to be also finite, in order to have again the error being just 1 over the number of samples of Monte Carlo squared. So then I can think of this as just a random variable that I will be sampling just using Monte Carlo, and I don't need to even know about the underlying multi-level structure. So again, the crucial bits here is that I have the cost and the second moment having those assumptions, the usual assumptions, but also that I'm only in the regime beta greater than gamma. Okay. So coming back to my problem, as I said, I have this expected loss, which is an expectation of a Lipschitz function of another expectation of this payoff, and I'm conditioning on the both the default time at tau, the default time and the market price at tau, at the default time. So first, I will need to be approximating both ST and S tau by, I'll use the Milstein scheme. And that is because I need, as I said before, I need this the second moment to be converging faster than the cost is increasing. So a Milstein scheme will give me this. An Euler-Marema scheme will not be sufficient. Will lead to well, not infinite, but a biased estimate, let's say. So the step size will be 2 to the power minus gamma L for this Milstein scheme. And then I can then, just like I did before with the unbiased multilevel Monte Carlo in general, for this payoff function, I can define a correction based on the approximation of S at L and L at L minus 1. And when, of course, L equals 0, I can only have the payoff at the courses level. So if the SDE has nice coefficients, then the Milstein scheme converges with a variance rate, which is 2 to the power minus 2L, while the cost for gamma equal 1 is 2 to the power minus L. So coming back to my result here, gamma will be 1, beta will be 2, and I get that, actually, I forgot to mention this, but the optimal probability is for selecting the level is 2 to the power minus L times the average between beta and gamma, and that's when gamma is 1 and beta is 2, I get that it's minus 2 to the power minus 3 L over 2. So that's the optimal probability. And then I can compute I can write the expectation, this one expectation here, as an expectation over the correction divided by the probability of selecting the random level. So this one now I can just use Monte Carlo to estimate, and there's no approximation, any issue with the approximation cost, because this random variable under the assumptions of the SDE, beta will be 2, as I said, gamma will be 1. So this will have finite cost and variance, and then I can just use normal Monte Carlo here to estimate this expectation. Okay, what about, so now that I replace this expectation, the inner expectation, by something which has no cost, what about the expectation outside? So the expectation outside requires two approximations, SH, S tau, well, I mean, SH is given, I should say, S tau, and the approximation with respect to, for this expectation here. So in order to approximate the expectation outside, every sample will need an approximation of the expectation inside and of S tau. So to do this, I'll just write down the expected value here, approximate the expected value using 2 to the power L samples, where again, this is just a Monte Carlo sampler with 2 to the power L. So here, this is my just random variable, which has finite cost and finite variance. And then S tau as well, I have to approximate it using Milstein scheme, again, for the same reason as before, with a step size 2 to the power minus L. So now my correction, delta F, will be the coarse minus the fine. Subject to when L is equal to 0, of course, it's just the coarse, just like before. But here, I'm approximating both the expectation with Monte Carlo and the stock price at tau at the default time, and similarly here at L minus 1 and at tau. And a crucial thing here that I'm doing, which is using an antithetic approximator for delta F, which is denoted here. So this means that I take the 2 to the power L samples that I use in the expectation to approximate the expectation here and split them into two parts of 2 to the power minus L, 2 to the power L minus 1. And these two parts, then I can compute the average, the Monte Carlo average on each one of these two parts, and then take the average after evaluating F. And the reason this is important is, again, for the same as using the Milstein, I need a variance convergence rate that is faster than the cost increase. And with this, I can prove that if F is piecewise linear, that this correction here has a second moment, convergence rate of the second moment, which has beta equal 3/2. And the cost, of course, is just 2 to the power L, because that's the number of samples. And this, the other part is that the Milstein scheme, or having the approximation of S tau, does not actually hurt anything. So I get that the optimal probability of selecting a level, a new level, which again, this is what I'll be doing, is I'll take this correction and randomizing the level, the approximation level here. So for this, I'll take the optimal level, the optimal probability is 2 to the power minus 5L over 4. And that comes from the fact that beta is 3/2 while gamma is 1. So the average is 5/4. And then I can write this expected loss in terms of the expectation of this random variable here. So now comes the main result of this work, which is this now random variable has two inner expectations with two unbiased multi-level Monte Carlo. And I need to prove that this one has actually bounded, has finite sampling cost and variance. So in order to have finite cost and variance, it needs both, as I said, the beta to be fast enough, which I used Milstein and the antithetic random variable in order to have that cost being, in order to have the unbiased multi-level Monte Carlo random variable having finite sampling cost and variance. And also there's a little bit more there in terms of proving it, because you will, if you expand this, you will have a multi-index structure. And for the multi-index structure, one needs to prove as well that it doesn't hurt essentially. And you use the fact there that f is, the function f is piecewise continuous, and also that the most inner expectation has bounded moments, or the most inner random variable has bounded moments larger than 2. And this I need, this higher bounded moments I need for the antithetic random variable to have a faster convergence rate in terms of the second moment. And if I don't have that, then of course, if I only have 2 moments, then I won't be able to get the better convergence rate of the antithetic estimator. This is an important point that I'll come back to in the conclusion, because it means that I have a limitation on how many times I can do this. But I'll talk about this in the conclusion part. Okay, so now I've managed to treat this expected loss in terms of just as an expectation of something which has no approximation whatsoever, except maybe for SH. But this one now has a, it's just like a Monte Carlo estimator. There's no problem with it. So now I can go back to my original problem, which is computing a probability of some random variable, this random variable, lambda of SH, being larger than L. So now this is the problem, and lambda of SH again is just can be approximated within some simple Monte Carlo estimator. So this again, I'll use multi-level Monte Carlo, but just to illustrate the issue here, if so I write the probability as an expectation, and then the correction again is the for any general x, which I approximate with XL. So think of this x as now the expected value of as lambda, being the expected value of this function, which is I have to approximate using Monte Carlo. So this now probability depends on x, and then I have to approximate XL, x with XL being a Monte Carlo approximation of x. And then my correction, I can write it in terms of the indicator evaluated at XL minus the indicator evaluated at XL minus 1 up to a course level. And then the same way as before, I can write the expectation in terms of an infinite sum. I have to truncate the sum here because I don't have the necessary convergence rates of beta, the second moment. So my beta is small. So I have to truncate this sum instead, and then approximate each one of these expectations of the corrections using Monte Carlo. And that's the celebrated multi-level Monte Carlo. In this case, I will be needing 3 assumptions in order to rigorously analyze the cost of the multi-level Monte Carlo estimator. Assumption 1 and 3 are the traditional ones. And again, notice that they are on, I'm assuming them on XL rather than XL minus 1, rather than on the quantity of interest, which is the indicator of X. So the bias converges like 2 to the power minus alpha L, the cost is 2 to the power gamma L. And this one is slightly more complicated one. So I'm going to be assuming that the difference or the error I'm making has finite moments of up to Q, where Q is greater than 2. So I need more than 2 moments. 2 moments is not enough. As in typical multi-level Monte Carlo, I only need here that the variance or the second moment is bounded and converges like 2 to the power minus beta L. Here I will need slightly more than that, Q moments in fact. And I also allow a positive random variable to scale my sigma, which I call sigma L, to scale this correction here, or this error, whatever that random variable may be. This random variable doesn't matter. As a matter of fact, you can choose it to be whatever you want it to be. as long as you can evaluate it. Okay, so with this, you have your traditional traditional complexity result for multi-level Monte Carlo, except that you will notice here, in order to get the optimal complexity, I need beta to be greater than 2 gamma up to this factor, which goes to 1 as the number of moments go to infinity, number of bounded moments go to infinity. I need beta to be greater than 2 gamma rather than beta, just gamma. And this comes exactly from the fact that making small errors in the in x here, so making small errors in xl and xl minus 1, if these are small enough and they are close to 0, I'll be making an order 1 error in the indicator function. So this leads to a reduced convergence rate of the indicator function, or the correction of the indicator function, and that one leads to this that beta has to be now greater than 2 gamma rather than beta greater than gamma, as you would expect. Okay, so this is now for my particular case. Again, I am computing the probability of this expected loss, and the expected loss can be written as an expectation minus this L, this constant L, which this is now my X, and I again approximate X using XL being an inner Monte Carlo sampler with number of samples to the power gamma L. I'll be actually setting gamma to 1 in most of the examples, but in general, it's to the power gamma L. And the sigma L I'll be using that I talked about before will be just the sample variance. And then for this, the assumptions will be holding for alpha equal beta equal gamma. So equal 1 if I pick gamma to be 1. And so the complexity result here, since gamma is 1, beta is 1 again, I'm in this regime here, and alpha is 1. So if you substitute those numbers, you get that the complexity is epsilon power minus 5 over 2. And so this is the issue. And again, it comes from the fact that the indicator function, making small errors in the indicator function leads to order 1 errors. And so the basic idea that we'll be using here is adaptive multi-level Monte Carlo, where instead of taking the correction to be the indicator function evaluated at XL and minus the indicator function evaluated at XL minus 1, I'll add a refinement factor here, eta L, which depends on the level. And this one will depend also on the value of X. So whenever I'm uncertain about the sign of XL plus eta L, I'll increase eta L. So I want to be, eta L is chosen such that I am certain enough about the sign of XL plus eta L. And the point is that I want to reduce the variance or the second moment of this delta L adaptive, which for the samples specifically of X that lie close to the discontinuity, while not adding too many samples away from the discontinuity. So in picture, this is how it looks. So I have my samples X, here are two samples of X, X1 and X2. And you see for the samples are away from discontinuity, I have here a Gaussian that represents my approximation, which again is scaled by the by my moments, by bounds on the moments, which is 2 to the power minus beta L over 2, times the sigma L, which again is we choose to be whatever it wants to be, whatever we want, as long as we can evaluate it. So for this Gauss, my approximation can lie anywhere within this Gaussian, while my exact value is here, but it doesn't matter because the indicator function, which I represent here in the back, will always evaluate to 0. So I don't make any errors. I don't need more accuracy in evaluating X1 here in order to get a better approximation of the indicator function. The only problem comes in when X itself is close to discontinuity, and then my approximation can lie anywhere it wants within this Gaussian. And in this case, it can lie on the opposite side, on the wrong side of the discontinuity. And then the indicator function will be evaluated here to 1, while in reality it's 0. And this will give me an order 1 error. But it only will give me an order 1 error in the probability regime when the X itself, this X, lies close to discontinuity. And this, of course, is assuming that the property is bounded, I can then bound this error as well. But then the key here is to refine this approximation with an additional eta L, which depends on the particular sample X2. And this one, I only refine this sample here, but I don't touch this one here. So the refinement is sample dependent. And doing this, I make sure that I control the probability of having the wrong answer in the indicator function. So this is the theory. In practice, what we do is we look at the absolute value of this X random variable at our refinement plus the additional refinement. So the absolute value tells me how far I am from the discontinuity being at 0. So if the discontinuity is 0, so it just tells me how far I'm from here. And we keep refining, we keep adding to eta L until we are sure, until we are far away from discontinuity subject to some factor here, which depends on an R, which is a tuning parameter. So this factor here is just, it controls the variance and the work to make sure that I don't pay too much work in my refinement, and I don't pay too much error if I make an error, if the X lies on the opposite side of discontinuity. So R is a tuning parameter. It's not actually a tuning parameter. It's just a parameter that one can choose, but we have explicit bounds on what are the values are that are acceptable for R to give me near optimal complexity of multi-level Monte Carlo. And we also force that this extra refinement cannot be more than L, and this will so I cannot refine more than 2L essentially, and this will bound the expected cost. The result is that this is the same result as before in the same complexity theory. And you see here the same factor Q plus 1 divided by Q, but now instead of 2 gamma, I have gamma. So beta again has to be only greater than gamma for this when using this adaptive sampler with a particular value of R, or for a particular range of values of R. Assuming I have higher moments than 2, that's all I need to get the optimal complexity. So beta only has to be greater than gamma when Q, for example, goes to infinity to get the optimal complexity of sub power minus 2. So in our case, we have beta equal gamma, and actually, as a matter of fact, because I'm using the sample variance, I can take Q going to infinity. So the cost is epsilon power minus 2 minus any nu due to this log factor and the fact that Q is fixed. So it's near optimal, and yeah, I recover the near optimal complexity that I would have had I not have an indicator function, but just a Lipschitz function instead, as an example. So I want to show you some experiments just to drive home the point about the adaptivity here. So I have here a plot of the cost per level for 2 different estimators, one using 2 to the power L samples in the inner expectation, one using 2 to the power 2L samples. So you see, of course, that the cost per level is just increasing as 2 to the power 2L versus 2 to the power L, as you would expect. And the point here is that for 2 to the power L, so that's in red, I'm doing too little work, and for 2 to the power 2L, I'm doing too much work. So it's clear here that for 2 to the power 2L or gamma equal 2, I'm doing too much work, but then I get my correct variance convergence rate, or my nice variance convergence rate 2 to the power minus L. While in gamma, I don't do as much work, but then of course I don't get as much variance reduction. I get only 2 to the power minus L over 2. So that's why I have my complexity epsilon power minus 5 over 2, regardless if I choose, of course, 1 or 2 for gamma. Now with adaptivity, what I do is per sample, I adapt between 2 to the power L and 2 to the power 2L. And overall, the complexity, the cost per sample is still 2 to the power L, but the variance convergence rate that I get that's in green here is as if I'm using 2 to the power minus 2L for every sample. And that's again by controlling the error in the samples where I do make an error. And so this, as a result, has this complexity plots where using too little work with gamma equal 1 or too much work with gamma equal 2, I get suboptimal results or suboptimal complexity of epsilon power minus 5 over 2. While using adaptivity, as I said, I get epsilon power minus 2 times some factor, some log epsilon squared. Here, before I had epsilon power minus 2 minus nu for any nu. But because I have here bounded moments for any Q, I can get as close as I want to this complexity. And this is what I observe in practice as well. Okay, so in my conclusion, what I want to talk about is issues with this methodology and our current work. So while we were working on this, and I remind you, the main components of this work is an unbiased multi-level Monte Carlo for both estimating the expectation and estimating the stock price. There were two works that were published, one by Said Wang and one by Zhu, Peter Glynn, and others in 2022 and 2023. And those approximate values or nested expectations like this. So here we have the expectation at level J is just expectation with a maximum. So that's my Lipschitz. That's my Lipschitz function evaluated at the next level of expectation and some function at the, here I'm just using Y for the stock price, but it includes anything as well, up to some final level T. And the particular application they had here is computing the Bermuda option, in which at for fixed time discretization, what one does is one compares the payoff that they would get at the time yj plus 1 or at time j plus 1 versus the payoff they would get at the end maturity, or the end of the payoff they would get at the next step. And then decide based on that if they want to make the call the option or not, or they want to exercise the option or not. So here we don't only have three quantities of interest, all of Lipschitz functions, but we have T levels of recursion or levels of expectation. All of them using this max function up to the final one, which can also use any function that is Lipschitz or has a bonus second derivative. So again, if we apply this to our case, we will need to use Mearstein and antithetic estimator to get the canonical complexity. And that's because every time we do that, we need to get an estimator with a finite cost and a finite variance. So we need sufficiently fast convergence rate of the second moment compared to the first moment, compared to the increase in cost. Now, the problem with unbiased multi-level Monte Carlo in general is that it has has a penalty on the bounded moments. So even if I use the best case scenario, if you look at the qth moment of a unbiased multi-level Monte Carlo quantity of interest, so that's just the expected value of this my new random variable coming from unbiased multi-level Monte Carlo to raised to the power q. So you can evaluate this by summing over all levels from L plus 0 to infinity times the expected value of the qth moment of my correction times this probability. So this probability comes the minus q comes from the fact that I have here PL to the minus q, and the one I have it from the fact that I have the I'm expanding the expectation. So even if I have bounded q moments of the correction of this multi-level correction, so I'm in the best case scenario when I have this q as bounded as I want it to be, bounded, let's say, in the sense of 2 to the power minus q beta L over 2. So I have usual bounds on the qth moments. This term will kill me. So this term here, I'm assuming that the probability is 2 to the power minus zeta L for some zeta. And so by substituting these two bounds, I get this infinite sum where I need this power to be negative. So the power being negative means that this is only bounded when q is less than this factor. And if I substitute the optimal value of zeta, q has to be less than this number here. So even if my corrections have bounded moments, the moments that are bounded, the bound on the moments in the unbiased multi-level Monte Carlo due to this infinite sum is only bounded up to beta plus gamma divided by gamma. So if you think of beta, let's say is 2, gamma is 1, I only get bounded 3 moments, even if my correction had bounded infinite moments. So what this means is that if I'm applying this nested expectation recursively, after I apply it the first time, I get 3 moments. And then later on, I'll have to apply it again, and I'll get slightly less than 3. And then later on, I'll apply it again, I'll get slightly less than what I got before. So the cost will, I will always have to be making, I will always be losing moments, and that will correspond to having to make a suboptimal choice of zeta. Because in order to have bounded at the end, in order to have bounded second moments. So that will be my objective in the end. So making suboptimal choices of zeta, this probability, means that the cost will increase with the number of recursions t. And that's exactly what was analyzed in this paper, in these two papers. And in fact, they show that the cost is scaling like 10 to the power t squared, which is a lot. Now, the key insight here is that actually using unbiased multi-level Monte Carlo is not required. We only did it because it was simple. It was simple to we already know how to couple Monte Carlo estimators. We know how to couple to do the antithetic Monte Carlo estimators, and that's why we chose unbiased multi-level Monte Carlo. But I can still come up with an unbiased estimator if I go back here by using the most outer expectation using unbiased multi-level Monte Carlo and biased all the way through. And this actually leads to better scaling in terms of t and the order of 2 to the power t log t rather than 10 to the power t squared. I focus here on the t squared versus t log t rather than the 2 versus 10. And the coupling of multi-level Monte Carlo is actually not very much more difficult than coupling Monte Carlo. One should just account for the additional bias. But if you analyze additional bias and analyze what happens there, you can also, instead of using Milstein, you could use Olio-Mariano throughout when these y's correspond to stochastic processes. And then the one can still get a complexity result even when using such methods. So you remove the need for Milstein, which comes with its own problems. Okay, so that's the current work, and the future works is both on nested multi-level Monte Carlo, as I said, but also I haven't talked about this, but there's also work on computing the value at risk, which requires solving an equation that where there's an expectation, so using some stochastic approximation method, and there you could use also adaptivity to speed up the computation, which is what we're working on right now. But in general, the key ideas that I would like to get out from here is that this hierarchical nested expectations or recursive nested expectations is actually not such a big problem, even though it's usually the main issue for all these computations by using these multi-level Monte Carlos. If you have limited number of levels, you can use unbiased multi-level Monte Carlo and you get decent results. Assuming you can use Milstein or similar methods. And if you have a probability like we do or a discontinuous function, then you would need to use adaptivity to regain the optimal complexity. Which will regain again the optimal complexity or the near optimal complexity of multi-level Monte Carlo. One key thing here that I don't talk about, which is the problems with computing these probabilities is the stability of the multi-level Monte Carlo algorithm, and that's due to the fact that the kurtosis, so estimating the variance becomes more and more difficult as L increases, and due to the increase in kurtosis. That can be handled, and we talk about this in our papers, which I should flash here. So we talk about in this paper with Spence and Teckentrup about strategies to deal with this at the algorithmic level rather than the estimator level. But of course, anything that can improve this kurtosis will be also great. The original paper, this is the paper, this talk is based on the paper Efficient Risk Estimation for CVA, which is still a preprint. The adaptivity is in this paper, and I should also mention these two papers about the recursive unbiased multi-level Monte Carlo. Thank you very much.
Thank you very much for your talk. Do you have any questions from the audience?
Thank you very much for this very nice talk, Abdul. I was wondering, there's to me, it seems related paper by Bourget, Gobet, and others about multi-level Monte Carlo for I think actually the main application is initial margin computations, but it's also this kind of nested conditional expectations. So I don't know, maybe you can comment on this.
So who are the authors?
Emmanuel Gobet, Florian Bourget, Stefano De Marco, and I think another author.
Right. No, actually, I wasn't aware of it. Thanks. Yeah, I came across this paper on unbiased. Was this published recently or?
Yes, it should have been published recently.
Okay. Okay. Yeah.
I think the preprint is from 2020, but
right.
sure
right.
when it...
Okay. I'll take a look at it. Thanks for letting me know about it. Yeah, I wasn't aware of it.
Thank you.
Any further questions?
Hi, Abdul. Thank you for a nice talk.
Hi,
I was wondering, so you mentioned it very briefly, this value at risk computations. So in that case, the discontinuity, or I mean, you don't know the quantile a priori, so you're calculating it over the iteration of whatever stochastic gradient and so on.
Mm-hmm.
So what would be the idea here for the adaptive case? So you
right.
adjust
Mm-hmm. So
please.
Yeah, so just to mention here, so the key there is that, or the problem there is that we don't know what L is, we don't know what the quantile is, but we are fixing this probability to be some fixed value. And so we propose one algorithm, which is, because we are dealing here with just simple CDFs, one could just look at the root of that function. And so when the function is nice behaving, and then you only need to figure out how to approximate this expectation with the probability. So one could use at every step of the iteration in a bisection method, use a multi-level Monte Carlo method, like I talked about here, to compute this probability, with a tolerance that is decreasing as you get closer and closer to the root. So that is one idea that we talk about in the paper. Now this one is one of the main issues with it is that it's difficult to analyze, and it's not the standard way of doing things. Normally what people would like to do is just compute this using stochastic approximation techniques, where you compute essentially one computes the difference between these two, and then find the root based on maybe some randomness, some random path in order to compute the expectation. So you evolve this state, and at every step you compute this this function here until you go to zero. Sorry, this function, samples of this function. And for that, the point is that if this one has an approximation, so instead of lambda you have lambda L. What we are looking at now is, for when using a stochastic approximation technique, when you have a sample and you compute this lambda at every step, maybe you want to compute it at the coarsest level, and only when things are close to discontinuity, again, you improve, you add the refinement level L here, there, in order to achieve a better approximation closer when you are close to discontinuity, just like we do it in adaptivity. The difference there is that, unlike what we're looking at here, where one has the just independent samples, the samples there are dependent, because they depend on the previous estimation of the previous estimate of L. So every time you are finding the root of that equation L, and then the next time you propose a new L, one has to compute based on the previous one. So you don't have this independent samples that we have here. And that's what we're working on right now in terms of the analysis. I suspect that it will be done by next month or so, in terms of the approximation, the adaptive version of the stochastic approximation technique. Don't know if that answers your question.
Okay, so we have any more questions? If not, let's thank Abdul again. Thank you so much.
Cheers.
So we resume at 13:30 with Emmanuel Gobet. Thank you again, Abdul.